You are watching the Cosmic Case Files, a forensic investigation into the universe's greatest puzzles. Some stories are never finished. They're just filed away. Welcome to Chronicles of the Obscure. In this entry, we investigate. Why did our Pioneer probes drift off course by a tiny, unexplained amount? In 1972, NASA launched Pioneer 10. Its mission, fly past Jupiter, then keep going. Out of the solar system, into the void. Carrying a golden plaque, just in case someone out there finds it. This plaque was humanity's first direct message to any extraterrestrial intelligence, a cosmic calling card, etched with images of a man and woman, our solar system, and the probe's trajectory. It was a testament to our ambition, curiosity, and hope for connection across the vastness of space. A year later, Pioneer 11 followed. Same mission, same trajectory, same golden message in a bottle. These twin probes were trailblazers, designed to endure the harsh realities of deep space, pushing the boundaries of our understanding. Their journeys were meticulously planned, their paths calculated with astonishing precision, accounting for every gravitational pull and push known to science. For decades, they worked perfectly. They sent back images of Jupiter, Saturn, and the outer planets. They crossed the asteroid belt, a region once feared as an impassable barrier, proving our technology could venture far beyond Earth's protective embrace. They kept going, silently relaying data across billions of miles, extending our senses into the cold, dark reaches of the cosmos. Each byte of data was a triumph, painting a more complete picture of our solar neighborhood. Then, in the 1980s, something strange showed up in the data. It wasn't a sudden catastrophic failure, nor a dramatic deviation. It was far more subtle, a whisper in the noise, a persistent anomaly that began to gnaw at the edges of scientific certainty. The meticulous tracking data, gathered by NASA's Deep Space Network, began to reveal a discrepancy, a tiny deviation from the predicted path that grew steadily over time. The probes were slowing down, not a lot, not enough to notice without precise measurements, but enough, a tiny, constant deceleration, about 300 inches per day squared. To put that into perspective, imagine driving a car for an entire year. The total distance lost due to this anomaly would be less than the width of a tire. It was an almost imperceptible drag, a phantom force acting on these distant metallic messengers. A force that defied immediate explanation, but it was there. And it shouldn't have been. According to all known physics, once these probes had escaped the dominant gravitational influence of the Sun and planets, they should have continued their journey at a constant velocity. This is Newton's first law of motion. An object in motion stays in motion unless acted on by an outside force. Yet they weren't. Something was subtly, persistently pulling them back. This unknown force, however minuscule, represented a crack in our understanding. A challenge to the very laws we thought governed the universe. The science behind. When you send a probe into deep space, its trajectory is determined by gravity. The sun pulls it. The planets pull it. These gravitational interactions are incredibly well understood. But once it's past them, it should coast at a constant velocity. This fundamental principle allows us to predict the movements of planets and send spacecraft to distant worlds with pinpoint accuracy. The Pioneer probes were designed to be perfect examples of this law in action, yet they seemed to be violating it. Pioneer 10 and 11 were being acted on by something, and no one knew what. This unknown force, however minuscule, represented a crack in our understanding, a challenge to the very laws we thought governed the universe. It was a scientific mystery of the highest order, hinting at either a flaw in our instruments, an oversight in our calculations, or most excitingly, a new, undiscovered aspect of reality. For 20 years, scientists assumed it was a glitch. The initial reaction to such an anomaly is often to look for mundane explanations. Perhaps it was leftover fuel venting, creating a tiny, unmeasured thrust, or heat radiating unevenly from the spacecraft, pushing it ever so slightly. They called it the Pioneer Anomaly, and mostly ignored it, filing it away as an interesting but likely solvable puzzle. But by the 1990s, the data was too clean to ignore. The deceleration was constant, unchanging. It wasn't erratic, as one might expect from random fuel leaks or fluctuating thermal emissions. It was a steady, unwavering pull, as if some invisible hand was gently pulling the probes back toward the sun. The consistency of the anomaly across both probes made it increasingly difficult to dismiss as mere instrumental error. Theories multiplied. The anomaly became a fertile ground for speculation, drawing in physicists and astronomers from various fields. Maybe it was dark matter, exerting a subtle gravitational influence we hadn't accounted for. Maybe it was a flaw in our understanding of gravity itself, suggesting that Einstein's theory of general relativity might break down at vast distances. Maybe there was something wrong with Newton's laws at vast distances. Maybe the probes were revealing a new force of nature. The possibilities were both daunting and exhilarating. In 1994, a physicist named Michael Martin Nieto started digging. He wasn't content with assumptions or dismissals. He gathered every scrap of data from the missions. Thousands of hours of tracking, millions of measurements. And slowly, methodically, he ruled out the obvious explanations. It wasn't fuel venting. The deceleration was too steady. It wasn't solar wind, too weak. It wasn't the probe's own heat radiation, at least not in the way initially conceived. By 2002, the mystery had a name, the Pioneer Anomaly, and it had no solution. It stood as a stark reminder that even with our most advanced technology, the universe still held secrets capable of baffling us. In 2005, a spacecraft called New Horizons launched toward Pluto. Engineers, keenly aware of the Pioneer Anomaly, designed it to test for the phenomenon. They built in extra fuel, extra tracking capabilities, extra everything, to ensure that if the anomaly was real, New Horizons would feel it too. It didn't. New Horizons coasted exactly as predicted. This was a significant blow to the new physics theories, as it suggested that whatever was affecting the Pioneer probes was unique to them, rather than a universal phenomenon. So what was going on? The puzzle deepened. If it wasn't new physics, and it wasn't a universal force, then the explanation had to lie within the probes themselves, or in the way we were observing them. In 2012, a team of researchers finally cracked it. Led by Slava Turishev at NASA's Jet Propulsion Laboratory, they went back to the original data, not the summaries, but the raw telemetry. This was an enormous undertaking, involving sifting through decades of archived data. They had to reconstruct the thermal models of the spacecraft with unprecedented detail, and they found something everyone had missed. The anomaly wasn't a force, it was heat. As the Pioneer probes traveled farther from the sun, their radioactive power sources, specifically radioisotope thermoelectric generators, RTGs, generated heat to produce electricity. That heat radiated out in all directions, but unevenly. Due to the design of the spacecraft, one side of the probe was always slightly warmer than the other, creating a tiny thermal imbalance. This subtle difference meant that more heat photons were emitted in one direction than another. And according to the principles of thermodynamics and momentum conservation, this tiny imbalance acted like a thruster, a minuscule but persistent push, gently nudging the probes back toward the sun. The effect, known as thermal recoil force, was precisely calculated and found to match the observed deceleration. Not a new force, not dark matter, not a crack in gravity, just heat, radiating into space, pushing back. The explanation was elegant in its simplicity, a testament to the power of meticulous data analysis and a deep understanding of spacecraft engineering. It was a triumph of conventional physics, demonstrating that even the most perplexing anomalies can often be explained by known principles. Case closed. The scientific community largely accepted this thermal recoil explanation as the definitive solution to the Pioneer Anomaly. It fit the data, it explained the consistency, and it didn't require any radical new physics. Except, the math only worked if the probe's heat radiation was perfectly symmetrical in one direction and asymmetrical in another. It required assumptions about how the heat spread, how it reflected off the instruments, how it changed over decades. Good assumptions. Reasonable assumptions. But assumptions. And here's the thing about assumptions. They're not proof. While the thermal recoil explanation was the best fit and widely accepted, a small contingent of scientists continued to question whether it fully accounted for every aspect of the anomaly. The universe, after all, has a way of hiding its secrets in plain sight, and sometimes even the most elegant solutions leave a tiny, lingering doubt. In 2020, a new analysis suggested the heat explanation might be incomplete. Researchers revisited the data, applying even more sophisticated modeling techniques. Their findings hinted that while thermal recoil was undoubtedly a major factor, it might not account for 100% of the observed deceleration. Maybe there was still something else, a tiny residual effect that remained unexplained. Maybe the anomaly wasn't fully solved after all. Pioneer 10 and 11 are gone now, dead, silent, drifting through interstellar space at 27,000 miles per hour. Their power sources have long since faded, their instruments are cold, and their golden plaques are the only active remnants of their incredible journeys. We'll never get more data from them. The case is as closed as it will ever be, not because every single question has been definitively answered, but because the primary sources of information have ceased to exist. But in science, closed doesn't always mean solved. Sometimes it just means we ran out of evidence. The Pioneer Anomaly stands as a powerful example of this scientific reality. It's a story of persistent inquiry, of challenging assumptions, and of the humbling realization that even the most precise measurements can hide subtle complexities. The Pioneer Anomaly taught us something valuable. Even the smallest deviation matters. A tiny deceleration, smaller than a tire's width over a year, led to decades of investigation. It forced us to look closer, think harder, question assumptions, and develop more sophisticated tools for analysis. It was a testament to the scientific method itself, a journey from observation to hypothesis, to rigorous testing, and ultimately to a deeper understanding of the universe. And in the end, it reminded us that space is not empty. It's full of heat, light, gravity, and mystery. Even where we think there's nothing, there's always something. The vacuum of space is not truly empty. It's a dynamic environment filled with particles, fields, and subtle interactions. The Pioneer Anomaly, in its resolution, revealed the intricate dance between a spacecraft's internal workings and the vast, seemingly empty canvas of the cosmos. Pioneer 10 and 11. Our first messengers to the stars. They carried a golden plaque and a secret. The secret is solved, mostly. The plaque is still out there, a silent ambassador of humanity, traveling endlessly through the galactic night. And somewhere, maybe, someone will find it. A relic from a distant civilization that dared to dream beyond its home planet, and in doing so, uncovered a subtle truth about the universe. This has been the Cosmic Case Files. The investigation continues. Next time, the UAP Pentagon Report. What did the government actually conclude about unidentified aerial phenomena? Subscribe and hit the playlist so you don't miss it.